So here we're going to be looking at what is known as the Simmons Smith reaction. The Simmons Smith reaction is a reaction that takes alkenes and through the use of diiodomethane as well as zinc and copper, ether here on the bottom is our solvent, we can convert an alkene into a cyclopropane ring. Now, the original way that people made cyclopropane rings was to use a class of compounds known as carbenes. Carbenes are fairly unusual organic compounds. They're carbons that have only two bonds and a lone pair. Now, if you calculate the formal charge here, the formal charge on a carbene is 0. So carbenes are neutral. In addition, they have an empty p orbital. And so while you can use carbenes to make a cyclopropane ring, instead of using the reagents we have in the Simmons-Smith reaction, in general, we don't do it that way anymore. And the reason is that carbenes are extremely reactive. And when the more reactive of a species or reagent that you're using in a reaction, the more likely you are to end up with the possibility of undesired byproducts, things that go wrong in the reaction. And so the Simmons-Smith reaction, first disclosed in 1959, probably not surprisingly, by Howard Simmons and Ronald Smith, both of whom were at DuPont. Basically what they did was they found a better way, a more controlled way to make cyclopropane rings. And so what happens in a Simmons-Smith reaction is that you start with your diiodomethane and your mixture of zinc and copper. If you add them together in ether, you end up with what we essentially refer to as an insertion reaction. And you can see what's happened here. We start with diiodomethane, and the zinc here has actually inserted itself in the middle, in between this carbon-iodine bond. And so this thing we have over here where the zinc is now inserted, we refer to it as a carbonoid. And a carbonoid, for our purposes, is basically a species that functions like a carbene, but is not quite as reactive and therefore a lot more controllable. Now, this is the structure that you'll see shown for this carbonoid if you look this up in most textbooks. And it's a decent representation of what's going on in this reaction. In reality, the species is probably a lot more complicated than this. But for our purposes, this is enough to represent what's going on. We also, in this reaction, the reaction is treated, based on electronegativity, as if that carbon-zinc bond is polar covalent. Alright, so now that we formed our carbonoid, what will that do? Well, the entire rest of the reaction takes place in a single step. The alkene attacks the carbon of the carbonoid. The carbon iodine electrons shift over to the zinc, and then the carbon-zinc bond, that bond breaks and those electrons come back to the alkene. And so in a single step, we formed a cyclopropane ring. As you can also see, this happens all on the same side. And so those two methyl groups stay in the same relationship as to what they were already. So that's the entire mechanism, for the Simmons Smith reaction. All right, what are some other examples? We can look at a couple of different starting materials. But in each case, these reactions are going to be very, very simple. The alkene will get converted into a cyclopropane ring. In this first example, we don't have to worry about any stereochemistry. There's no chirality, no chiral centers there. In the second one, we do have these two methyl groups. And it's just important to note that those two methyl groups, there's not going to be any preference for whether they point up or down, but they both need to point in the same direction. And this last example, again, that alkene will convert to the cyclopropane ring. So where might we find one of these reactions? Well, the fact is, unlike a lot of other reactions, applications for reactions that make cyclopropanes are not as numerous as many of the other reactions we study. The main reason for that is we just don't see a lot of cyclopropane rings in nature. They're too sterically hindered, they're not very stable. But there are cases, such as the following, where they are especially useful in organic synthesis. There are a few compounds out there that have cyclopropane rings, which do have biological purposes. And so, for example, this molecule we've drawn here is going to be an example of that. If we start with this, that alkene can undergo a Simmons Smith reaction. And then through a number of other steps, we're not going to walk through all the remaining steps, this compound eventually gets converted into its final target. And finally, at the very end, you can see the cyclopropane ring that was made in the Simmons Smith reaction is incorporated over here. So what is this compound? This is known as cilastatin, the final product. And cilastatin is an inhibitor of dehydropeptidase. And cilastatin is part of the drug Premaxin, which is a drug that can be used to treat severe infection of the heart and kidneys and other organs. So what other functional groups should we be concerned about when we're trying to run a Simmons-Smith reaction? Well, the fact is that carbonoids can be very, very reactive, and so we want to limit as many of the other functional groups as possible for these reactions. You'll notice in this synthesis of cilastatin, this piece doesn't really look anything like the rest of the molecule. And that's because this group here with these two oxygens is actually a group that's hiding the carbonyl. And most likely that's because there were some concerns, or maybe they actually tried it with the ketone there, or whatever carbonyl group, and they ran into problems trying to run the Simmons-Smith in the presence of the carbonyl. So when it comes to other functional groups, definitely a reaction that you want to be careful with, but also not a reaction that we use that often. Again, cyclopropane rings, not the most common functional group that we find, but if you need to use one, this is by far the best and most well-known method for it.